So hello everybody and welcome to this linear regression practical. You remember that we had this in the last course, basically, that we had in one of the previous videos. I told you about basically about how to perform regression. Today we will put this into practical with our little data set that, as always, we find at this URL here. It's the same data set that was used in the prior sessions. You can download this over here. We will use this data set, so some features of this data set that we will go into in order to perform the regression here, and see how you can use all this and how this all works, and how you basically in scikit-learn you can perform a regression, how you can use the R2 score, and so forth. So let's go into this. We use basically the pandas library as always in order to import our data set. We at the same time use NumPy in order to work with certain things that we will need later on. You know already both libraries. Let's import them, and let's import our data set. So our data set, basically, we import the data frame. You already know how this works. Read CSV file, and we have our data set, which is called train data clean CSV, and this is our data set. Okay, I can then remove all this here and open this little data set in order to get this here done. Okay, so fine, so good. We have our data frame. When I go into our data frame, we see here that we have these columns here, and basically what we will find out is that some of these columns are kind of have a linear relationship. I've already shown you last time this kind of correlation functionality, so I can use this core here in order to get the correlation between these points. And what we basically want to do is we want basically to see if these, how should I say, these parameter values, this parameter 0 here, we see that we have rather high correlation values, basically with radius 1 and radius 2, and we want to use this in order to build kind of a regression system which allows us to take radius 1 and radius 2, and in order to predict the parameter 0. Yeah, so this is kind of the exercise here. We will see that we basically can use here the radius 1 and the radius 2 in order to predict this value here. Kind of counterintuitive. Okay, the last time we kind of predicted does the patient have cancer or not. Here we will kind of predict, okay, what happens, for instance, if we have a missing value in this parameter column. Can I add a new value for this parameter column? Let's do it as simple as this. Yeah, so we want to predict from two values. This is our target here. This is in this case our y column. Radius 0 and radius 1 will be our x column. Okay, our x matrix if you want to. So how do we build this? Very easy. Before we build this, basically just also perform a little plot, so we can basically show this. So we can have, let's import the matplotlib. You already know this too, and here basically we will just perform a little plot that show these two plots here. So if I go here, plt scatter, and then I can do something like data frame, and I can do something like radius 0, as we've seen, just not to make it wrong. So we want to have radius 1, parameter 0. Okay, radius 1 and radius 2. Okay, so radius 1, we skip radius 0, as we see that here with radius 0 the correlation is rather low. Okay, so quick overview, df core gives us Pearson correlation between the columns. Okay, very easy. So we have df1, and we want to plot this. In order not to get into issues, it's always a good idea to convert this to NumPy arrays. It's not forcibly necessary. but it kind of helps you out in order to have the right shapes, in order to reshape things and things like this. Okay, so radius 1, perimeter 0. So how does the radius 1 behave in comparison to perimeter 0? So we plot radius 1 on the x-axis, perimeter 0 on the y-axis for each data point. Okay, as easy as this is done, and we see that there is some kind of linear relationship that we can basically find between these two. And let's see, for instance, as I said, if we miss out, for instance, a perimeter value in a data set like this, we could replace it using a little model that we fit it like that in order to replace a missing value. Yeah, this is something that you can do, for instance, instead of replacing it with mean values or things like this, in order then to build a better model from your data set. Yeah. Same thing here, radius 2. Let's do the same thing here with the radius 2 here. The parameters on this axis, we see if we do this scatter plot again, we have this kind of linear relationship between the two. Very, very interesting to know, and basically we can use both of them in order to predict the parameter 0 value. Okay, and then we will check in what kind of limits we can do this, how well our fit is. You see, of course, that this is not perfectly linear, that there is a lot of space between here, and we will kind of measure this with this R2 score that we had the last time, how well our fit basically behaves. Okay, so far so good. How will we do this? We talked the last time basically. So first of all, we will of course build our data set. So we will get this radius 1 and radius 2 into our x, yeah? So into our feature matrix, and then the parameter 0 into our y. So how do we do this? So we basically visit x, and we can easily do this in creating, for instance, a new data frame. Just to recap this functionality, that you can generate a data frame basically from a dictionary. So we do here radius 1, and we can say data frame radius 1 and we have the radius 2, and we see here that we can take the data frame of the radius 2 in this kind of dictionary nomenclature here, and you can see that in the dictionary, of course, behaves like a list, and you see basically, okay, you can use here this NumPy array stories here. Probably possibly not necessary, but this makes it kind of easier to have this here without, as I said, this to NumPy. It allows you to easier reshape things afterwards and things like this, instead of handling the whole data frame. Anyway, we create a new data frame out of these two columns. Yeah, that's what we do here. Okay, there it says it's an incomplete input. What did I do wrong? I will just double check here. I missed this one out. It's fine. And we have our x, and right now we need our y, basically our targets. So these are our features. We don't need to rescale them. We see that they are kind of in the same dimensions, which is very convenient for what we want. Yeah. So again, the y target is our data frame. Basically the column, which column is it? Parameter 0. Yeah, this is what we want to do. So we want to have radius 1, radius 2, and we want to predict parameter 0 from them. Okay. We have our targets here. Okay, so these are our features. We have two features. We perform a linear regression in this case, yeah, but a special linear regression because we use the elastic net, as I said, basically by injecting into this regression loss function these two parameters. So just recap this quickly from our slides. I brought up here the slides so that you can see this. So we went through this model. If you remember, basically we had this rich, lasso and elastic net. So this is the formula. This here is our regression formula. So this is basically, okay, the term that we will minimize. So we will minimize this distance here, okay, between basically these here are the predictions. This is our y value here. This here is our distance. And we have here lambda 1 and lambda 2, the rich term, and the lasso term, as I outlined in the last lecture, okay? So basically, okay, this here is how far I'm away from my fit, okay? And then I have basically, I add here to this loss function, basically I want to have here with the rich term small parameters, small model parameters, and I want to select as few model parameters as possible with this lambda 1, yeah? And we can shift between this lambda 1 and lambda 2. We can add arbitrary values for this lambda 1 and lambda 2, and I will show you how you do this, how you use this in scikit-learn, how we basically can use these two parameters in our linear regression that we perform here. Here we have the normal basically chi-square term, and here we use this, we add these two terms, and then basically scikit-learn will perform a fit according to this loss function with this lasso and rich term in this most basic case, linear regression, yeah? Okay, multiple linear regression because we have two input values, okay? Okay, so far so good. We have our x values, our y values. Let's perform something. Let's go to the regression. How does the regression work? For the regression, we use the elastic net. So from scikit-learn linear model, import elastic net, and we have our elastic net basically here. We say, okay, we use then we perform a regressor, so we call this, I call this not classifier as last time. I made a spelling mistake here, so regressor, and we call this here elastic net, and we say here alpha, and I will show you what the alpha value is. So I will use alpha 0.5 and L1 ratio also 0.5, and let's see what will happen, and what this alpha values, what this mystical alpha and L1 ratio values are. Yeah. So practically speaking, if you go into the scikit-learn documentation and you look it up here as scikit-learn linear model elastic net, you search a bit on the internet, you will find this website. You have basically that this is the formula that it uses for the loss function, yeah. And if you look at this is very easy to understand. So if we compare this to our formula that we had here basically, if I bring this up like this, let's make it like that so that you can see me too. Here we had basically this L lambda 1 lasso term and the lambda 2 rich term. So this here is the typical linear regression formula, okay? So here are our features x, this is the y. We have here basically this this vector here, which gives us, which parameterizes our linear regression. And we have here, this is this df y, okay, if you want to, yeah. And then we have here, this here is then lambda 1, and this here is lambda 2, okay? In scikit-learn, the nomenclature is a bit different. They give this an alpha value, which goes to lambda 1 and lambda 2, and then you can use this L1 ratio term in order to shift how much you want basically of this alpha to go into the lasso term and how much you want to go into the rich term. And you can see that basically you can get any type of value with this, because it's just this alpha multiplied by this L1 ratio, and here it's alpha times 1 minus this L1 ratio. They also use this 0.5 term here in order to perform this basically this these to model these two objects here, which are lambda 1 and lambda 2. Instead of using lambda 1 and lambda 2 directly, they use this alpha and L1 ratio terms here in order to shift basically from the lasso to the ridge. This is kind of how it works. Okay, so far so good. We will use this in our system here and have basically here this elastic net going on. Okay, so as put here alpha to 0.0, 0.5, the L1 ratio also to 0.5, and let's perform our elastic net regression. So how does this work? We already know this from the classifier, so instead of TLF for classifier, I just write here reg, as I want to call this like a regression, and this of course works with this fit functionality. And we use the x, as I said, the 2 numpy. It helps me to avoid kind of these shape errors. And if I have it in the wrong shape, as it's in a numpy array, then I can just reshape it as we have seen in the first lecture, of this course. So we do this here, we fit our story, and we get out that this here is our elastic net. Okay. So far so good. We have this here, and we will then basically we have our fit, and then you can use this in order to perform a prediction. So let's say what kind of values did I have here for this here? So let's say here 14, because we have 13, 14, 15, 16. Let's say I have for both 14. So radius 0, 14. Radius 1, 14, and 1 would be the outcome of this here. If I make this prediction, I would get a parameter 0 of 91. Okay, radius 1, radius 2, parameter as an output. Okay, typical regression. So basically, okay, I have two input values, I predict an output value. This is a typical regression example, in this case linear regression, using this elastic net functionality with the lasso and the ridge term, as I've shown you in the last lecture. Okay, fine. This is all fine. Right now we just performed the regression. We have no idea how good these values are, how good this prediction is. We get a very nice prediction, which is kind of in the values of the y's, with a new value that it might be in the training set or not. We didn't do a training test set split that we should do. We did not do cross-validation, as I've shown you basically with the classification examples. Here in the regression examples, okay, we need to perform some kind of cross-validation. I've shown you the R2 score. We want to use the R2 score in order to validate this story. Just to remember what the R2 score is. So as I told you, basically we take the mean of these values. In this case this would be a plane, and we get these squares here. So basically how far am I from this plane to this point. I calculate the squares, then I perform my fit. So I have here my surface. This is a linear fit, so I have a linear surface. And in this, basically, then I hope that these squares here are, so the distances to this surface squared is of course lower than here, and if this is lower than this, then basically the sum of the squares here is lower than this as total, and hopefully I get something close to 1, or at least better than 0, hopefully not negative. Okay, this was already described in the last lecture. We will use this here for the cross-validation. Okay, so how can we use this? How can we perform this? So we use from scikit-learn, we need to import a lot of stories. So model selection, import. What do we need? We need the cross-val score. You already know this from the classification story. We need the shuffle split that we will use, and we will do a train test split in order to build the final model. Okay, so fine, so good. Then new for this story here, for the regression story, we need the R2 score. Okay, in order to have a tangible score on how well our fit behaves, how well our prediction model behaves. And we need a make scorer function basically in order to be able to use this R2 score with this cross-validation score system here that we have in scikit-learn. Okay, we imported all this, we perform our cross-validation, we will use a lot of folds in this case, we use the shuffle split, and in order to get nice statistics, let's do a lot of splits, because we will need them probably, as this here it will fluctuate a lot. Yeah, we use the train size of 0.5, test size also 0.5. Let's do this. Well, let's do in this case here 0.6, 0.4 in order to do something a bit different. We have very few values, but I guess if you look at this, if we take 60%, basically we should be able to predict the next 40%. This is kind of what we want to do here. Okay, so fine, so good. And then we have our cross-validation. We need to build a scorer. So we say our scorer, and you can look it up in the functionality of scikit-learn. The way this works here is you have to build this scorer with the R2 score so that you can use the R2 score in the cross-validation. Okay, so fine, so good. And right now we want to cross-validate, and at the same time we want to model select. Yeah? So we want to use, if we go to our slides, good lambda 1 and good lambda 2 values, and we want to find some lambda 1 and lambda 2 values, and at the same time here of course not lambda 1 and lambda 2, because here in scikit-learn this works with alpha and L1 ratio, but we will use this alpha and L1 ratio in order to model the L1, lambda 1 and lambda 2 that we have here, and in order to find basically good values for our fit, and hopefully we find a good fit. This is kind of the story here. So how can we use this? Let's take these alpha values, and let's take these alpha values. Let's do something like this. Let's do something a bit, how should we say it? Let's use it logarithmic like this. So let's do here 1. We can do 2, 5, 10, something like this. Let's stop here. And then this is basically very big already, because if we go here in our values, if we would have rescaled this to 1, but our values here are rather huge. So let's keep pick the alpha value a bit higher to have some fun with this here. And let's take the L1 ratio. For the L1 ratio, it's basically very easy. So we do 0.25, 0.5, and 0.75 in order to shift this between this alpha, basically between lambda 1 and lambda 2 here. Yeah. Okay. So fine, so good. This is what we do here. And then we want to loop over all of this, so let's build a double loop. This is kind of a grid search problem. So we want to find good alpha values and good L1 ratios. And we perform our elastic net. So we train our regressor, and the regressor always has new hyperparameters. So in this case, basically it is alpha and L1 ratio values. Okay. Scores. The scores basically here, it's the new story. We have to use our scorer. So we use the cross-validation score with the new scorer as the last time. So we have have basically the regressor, we have here x to numpy and y to numpy in order to avoid any issues if this might be in the wrong shape. We do the cross-validation equals the cross-validation that we have created here. So here we do a lot of splits in order to get very nice statistics out. So 100 times we select 40 different percent or 40 different percent as a test set. We automatically jump them out. We know how this works. Basically we do this folds. Here we don't have so many values, we only have 200 values, but basically at random we select always a different subset with a lot of permutations basically going on, what we use as a training set and what do we use as a test set. Okay, nice. Scores. The next thing here is we want to print this. We want to know what are our scores, for which alpha, what do we get. So let's write here alpha, and we say here, you already know this from the model selection story. This is kind of analog to the model selection, but just that we have here one model with hyperparameters. I use here the /t, it's like in C notation a tabulator, in order to get basically this indented right, and so that it looks a bit nicer when we put it out. Okay, so far so good. I can use here plus, and then I will do here basically the L1 ratio like this. This is then already a string. Let's get me a space here, and then we do the scores like this, likewise like this. Let's put the tabulator here, and let's get here okay, and you can do something like plus minus. Use as last time the standard deviation in order to get the standard error, something like that. No? Okay, that's all nice. I want to keep the score so that I can find the best score very easy. So we can do something like my scores like that, and then we want to have my scores. This is an empty list, and to this empty list we append basically our scores, our mean, just the mean, because we can then find the standard and basically find the nice values that we want. I will perform a print like this just to get a new line. That should be all fine, and we run this right now. Okay, so this is basically how you perform cross-validation together with the R2 score. So you have to build the R2 score with the make scorer here, use it here in this crossval score, which we did not, but just to add it here, scoring, this is the important part, use our scorer, so that we have the R2 score. So here we use the R2 score that we have built here with our scorer in the cross-validation. This is the new part, the important part, basically how to score, how to perform cross-validation if you use a regression example. Okay, so far so good. Let's run this, and hopefully we get nice values out. And we have a spelling mistakes because this here is scores, that's fine. And we get our values out, very nicely written here. And we see that basically this alpha and L1 ratio does not help a lot for this little system here. But just to get you out, what would you do if you get highly different values? I mean, we get some different values, but as we see, the standard deviation or the standard error basically here is rather high. So if we see here, this is here between 0.5 and 0.7 here for this how should I say it, R2 score. These values are not too bad, to be honest. So if you look at this, so it says basically, okay, my squares are, so this term here is about 0.5, so I'm at least way better than the mean. If this here is 0.5, so this here is kind of how should I say it, well, at least this here is kind of 2 times the size of this one, yeah, if you can say it like this, yeah, so this is 0.5, it's kind of 1/2 here, so from this size, so this here is 2 times bigger than the fitted part, okay. This is what we get here, I mean, even better, because it's maybe 0.6, 0.7 sometimes, so we can say it's 2/3, let's say it like this. If it's 2/3, so we can say, okay, this here is 2/3 times bigger of this here than this here, okay. So fine, so good, okay. These are our scores. We have here, of course, plus minus 15, okay, it's not so nice, it fluctuates a lot in our cross-validation. This is why I used a very high, how should I say it, a very high number of splits in order to get this down here, but as you see, it fluctuates a lot, yeah. That's the story here. As I had this with the scores here, if I go to my mean scores, of course I get all means out here in a list. I can, as we have the NumPy library here, something that you can do is here very easy, is you can transform this into a NumPy array and say I want to have the maximum here, and then I get it's 0.684, and then I can look here, 0.684, where is it, 0.684, and we could basically say, okay, I mean, not really, because our fluctuations are really high, but we can basically say that these values here, so alpha 5, L1 ratio 0.5, gives us the best scores of the values that we have selected, okay. And then you could basically train a model with these hyperparameters, get something like this out and see if it works. This is something that we will do, yeah. So far so good. We do our train test set split as always, and then train the final model, and that's then will then basically be it. But let's do this here. So we do x train, y train, x test, y test, and then we do the train test split that we have here. I will just copy paste this here to be a bit faster, and then we can say, okay, what do we have here? Our x2 numpy and our y to numpy, which is of course the parameter. So these are the two radii, and this is the parameter here. And then we said, what did we have here? Test size and training size. So we use this here, train size, test size 0.46, 0.4. I copy paste this here. And we have it. We have our train test set split, and we can fit our final model basically and test it basically out, and this will then be our final model. So elasticnet, what is basically the good alpha value here? We said it was 0.5, so let's use alpha. And as I made this very nice, I can just copy paste this from here. is our final regressor model here, and then we can do final and yes, X-train. And what went wrong here? I guess this is here basically X-train. This is here the correct. I'm sorry for this little spelling mistake up here. This is the right way how it works. We have here the final regression, and we fitted it, and then we can basically show with the final regression with the predict functionality that we have here if we use the test set. Sorry, the score. And we get the score out of 0.64, which is not as nice as the one that we had, but we gave it basically, as we said here, in this training tested split we were with plus minus 11. So as said, basically these values are kind of all the same. So the alpha and the L1 ratio in this case here doesn't have so much of an impact, as our system behaves pretty well, and we kind of don't really, this kind of, how should I say it, this kind of rich and lasso regression doesn't have so much an impact. But basically in this overview, this is kind of just a story on how you can use this, how you can perform a regression, how you can score a regression with the R2 score, how you can use the R2 score in a cross-validation in order to find the right model. Here basically we see that all the model scores are kind of the same. We are kind of have shown how to find the best one and how to fit it, and the best one is of course in the neighborhood of what we expected, but we get here basically 0.64. That's the way it is. This is kind of what we built here, and we can use this final regressor in order to predict from the two radii a new perimeter value in our data set. Thank you so much. We will end here. Have a nice evening.